So with that, let's go to science. And so I would like to tell you about the symmetry of quantum gravity. But before we get into the subject, which will come in the second half of this talk, let me, so since this is meant to be not only for physicists, but for people in theoretical science broadly, so I thought I should first start with some discussion on quantum gravity in general. So in particular, why we do this kind of thing. So what I would like to tell you today, at least for the first half of this talk, is to discuss why the unification of general relativity and quantum mechanics is so difficult. The superstring theory, which is the subject of this winter school, is supposed to be the prime candidate for this question, but why is this so difficult? And in particular, why superstring theory is important in this context? And what is a holographic principle, which I will be utilizing later? And in particular, I would like to tell you what is known and not known about quantum gravity. So delineating this distinction is important. So first, let me discuss why the unification of general relativity and quantum mechanics has been difficult. So it is often said, and when you ask somebody, that standard answer you get is that, well, if you start with this Einstein gravity, which consists of maybe cosmological constant and Einstein-Hilbert term, and matter field with finite number of matter field, then such Lagrangian is not renormalizable by naive power counting, and so we cannot use it to compute quantum gravity effect reliably. So this will be a standard answer, but this actually is a little bit too quick, and it's not the whole story, so I would like to tell you a little bit of more nuanced story to it. So the reason for that is that, for example, there are many other non-renormalizable theories which are nevertheless useful even quantum mechanically. So for example, this is a Lagrangian for action for the pion theory in nuclear physics, and pi is a sort of SU2 vector which is captured by this Lagrangian. And this theory is also not renormalizable. F has a dimension, it happened to be 184 MeV. But it turns out that this actually Lagrangian action is very useful. You can use it to study phenomena, various reactions involving pions, as far as the energy and momentum scale involved in the process is less than F. And you can compute the quantum effect reliably. And in fact, one of the problems with such non-renormalizable theory, people say, is that you need infinitely many counterterms. But actually, there is some nuance to this story too. Because if you expand physical observable in power of energy and momentum, then in each term in this expansion, you actually only need a finite number of counterterms. So that means that as far as you do this kind of expansion, assuming that energy is much smaller compared to F, then you actually can systematically calculate things with at each order only finite number of parameters. So to actually appreciate this, let me remind you of Wilsonian view of renormalization group. So the pion theory is, of course, not a complete theory. It's not renormalizable. And in fact, you can think of this as some kind of low energy approximation to more complete theory, quantum chromodynamics. And quantum chromodynamics, because it's asymptotic free, can in principle be a complete theory. And in principle, pion theory, therefore this effective, this Lagrangian, this action, can be derived by doing QCD functional integral while keeping this low energy degrees of freedom for the pion. And so you can in principle consider deriving pion Lagrangian in this way. So this is the idea of effective theory. And for this effective theory, these kind of effective theories, therefore, are not fundamental theory and typically are not normalizable. However, to derive some low energy prediction, you can still use it, and you can use it including quantum effect. And in fact, many of the calculation of pion Lagrangian has been verified even experimentally. Einstein gravity, in this sense, is also, we think, is an effective theory. We think that there is a more complete theory that we can do any calculation, not just low energy low energy approximation. And so it is an effective theory, but just like the pion theory, provided that energy and momentum are less than the cutoff scale. In the case of gravity, of course, this is a Planck scale. And so when you have cutoff scale, then it's some threshold for low energy effective theory, which sort of tell you that how useful the theory is until which energy. And so this is some kind of threshold above which a more fundamental theory is required. Like pion would be useful until about 180 MeV, beyond which you would need QCD, for example. So Einstein gravity can be used to make reliable prediction as far as the energy scale is much below the Planck scale. And in fact, for example, Hawking's calculation of black hole radiance was based on semi-classical quantization of Einstein gravity coupled to matter. And the fluctuation of cosmic microwave background radiation has been computed as derived as a quantum mechanical effect during the era of inflation. And so these are, again, reliable calculations which can have even be tested experimentally. And you can even calculate, for example, corrections to Newton potential. So this is the Newton potential that we ran in undergrad. And then there is a relativistic corrections. And then there is one loop effect, and you see there is even H bar. And this can be calculated by just Einstein gravity coupled to point particles. And you can actually get some number out of it. So it's not true that Einstein gravity coupled to finite number of matter field cannot be used to calculate quantum effect. But there is some limitation, as I have emphasized here. So there are problems. So there are actually beyond this standard problem that this is a low energy effective theory. So can only used for effect whose energy is much less than the cutoff scale, in this case Planck scale. There are problems that are specific to quantum gravity. So let me mention a few of them. So in the case of general relativity, the energy cutoff can depend on observer. So from the perspective of one observer, you may have an effect whose energy level is much below the Planck scale, but that may depend on the point of view of observer. So this issue can be related to this more recent problem of black hole firewall, for example. So this kind of problem can be actually an issue in quantizing general relativity. Also, since we are looking at effective theory, so there are effects that are very intrinsic to theory which we miss. For example, if you are looking at pion theory, you will never have guessed that strong interaction has asymptotic free property. You have to go to QCD to see that. Oh, that was a third problem. And but there is also a second problem. That is that in the case of a pion, we can actually confidently do various calculations because eventually it is embedded in ultraviolet complete theory, which in this case is QCD. Do we know that Einstein gravity coupled to matter field can be embedded in consistent quantum theory of gravity eventually or not? And actually, one of the points I would like to make in the second half of this talk is that there is actually, at this point, there is a distinction between the standard quantum field theory and the quantum gravity. In the case of quantum field theory, Wilsonian philosophy is that you can write down any Lagrangian, as far as low energy Lagrangians are consistent with symmetry and the power counting property of momentum and energy. You can write down any term in the low energy effective theory, and you can hope that such low energy system can be embedded in a consistent quantum field theory. We have reason to believe that that may not be the case in quantum theory of gravity. That if you write some generic low energy effective theory coupled to Einstein gravity, such Lagrangian may or may not have ultraviolet completion. And there are a couple of evidences to suggest that that may be the case. So in that case, it's not actually guaranteed that the Einstein gravity-coupled matter field can be UV completed. So this is something that one should worry about. And the third problem is something I already mentioned prematurely, that is that there can be intrinsically quantum gravity effect that we would certainly miss if you are just looking at Einstein gravity. So in the case of quantum gravity, there are questions that we would actually like to address, such as the fate of evaporating black hole, or whether inflation model that cosmologists use can be derived from top down from more complete theory, or what is the origin, or what is the nature of the initial singularity of the universe. So those questions cannot be addressed by just using Einstein gravity-coupled matter field. Those are intrinsically a phenomena that goes beyond the Planck scale cutoff, and so you need something more than low energy effective action in that case. So let me take this second point, that is that is Einstein gravity guaranteed to have ultraviolet completion? So, in fact, we have some kind of existence theorem that such UV completion exists, and that is a string theory. Because superstring theory, one can actually calculate quantum effect without UV cutoff, so it is a consistent quantum theory. So it's UV complete in some sense. And its low energy effective action contains Einstein gravity. And by compactifying the space-time dimension to 4, then it has all the ingredients that are necessary to construct a standard model of particle physics. So, in this sense, we have some kind of existence theorem that Einstein gravity coupled to some type of matter field can be UV completed. So that actually gives us some confidence to proceed. And so that's one of the reasons that superstring theory is important to begin with, that it gives us this kind of confidence to proceed. And moreover, understanding quantum gravity beyond Einstein gravity coupled to matter is important because it actually gives you a special place in the hierarchy of physical world. So when we learn physics, we learn that physical world has a hierarchy of scales. So you have atoms, but atoms are made of nucleus with electron going around. Nucleus are made of protons and neutrons are made of quarks, so you have this kind of hierarchy. But there are reasons to believe that once you get to the ultimate unification of all forces, including gravity, then this type of hierarchy will terminate. So that's a special place. And so this by itself would be worth exploring. So that's another reason that superstring theory is interesting. So to highlight some of these ideas, let me discuss the issue of black hole paradox and emergence of holographic principle. So this is sort of a standard explanation of Hawking radiation. So suppose you have a black hole, and here I'm drawing this kind of diagram where the time goes vertically and space goes horizontally, and the light travel in 45 degrees. And so it's natural to draw event horizon in 45 degrees along the light ray. And without black hole horizon, then when particles are created, they pair produced. When they are pair produced, particle and antiparticle has energy, so they have to be pair annihilated, like this diagram. But if you have event horizon, inside of the horizon, time flows in a different way, so that the antiparticle here can have negative energy, so which enables the pair-created particle to escape black hole. And so that is the effect of black hole radiance discovered by Hawking. And then he utilized the formula for the temperature of black hole derived in this way to derive the formula for the entropy, which turned out to be proportional to the event horizon, the area of the horizon of the black hole. So this was a very interesting formula, that entropy of black hole is not proportional to the volume of the black hole, but proportional to the area of the event horizon. So entropy we learn in undergraduate thermodynamics is an extensive quantity, so it should be proportional to the volume. So why is it that it is proportional to the area? So this leads to the idea of holographic principle by 't Hooft and Susskind, that the fundamental degrees of freedom for a given region of space-time are defined not in the volume of that space-time, but degrees of freedom residing on the surface surrounding it. And in fact, it turns out that this surprising idea of this holographic principle is realized in string theory. So I would like to tell you in the next few slides how this idea came about in string theory. So to explain how the holographic principle that I sort of briefly mentioned over here is realized in string theory, I need some preparation. So that's going to be the next few transparency. So in string theory, there are open strings and closed strings. So there are two types of string. Closed string don't have end. Open string has two end points. Now, when you have open string, the end point can be in a various kind of subspace of space-time. Of course, end point may not have any constraint at all. It can end on anywhere in space-time. But you can also consider a situation where end point of open string are restricted to some subspace of space, such as two-dimensional surface or curve or point. And it turns out, as I will show you in the next slide, that these subspaces carry energy, or in the case of surface, tension, and emit graviton. Because if you have object with mass or energy concentrated, localized in some part of space-time, that can emit graviton or absorb graviton. So to see that, let us consider the following kind of diagram. So suppose you have this subspace where open string can end, and suppose you have closed string coming from the left. Well, so you have closed string coming here, but since you have this surface where open string can end, so closed string can open up, and this part can end, and then reconnect it and propagate in this way. So you can certainly consider such a diagram. But if you can draw a diagram, once you draw such worldsheet diagram, you can see it in different ways. Rather than seeing as open string with ending the end point on the subspace, you can look at the same diagram and think of it as closed string emitted from this surface. So that means that this surface on which open string can end can emit or absorb closed string. And in string theory, among states in this open string sector, closed string sector, are gravitons and other particles. So in particular, this diagram shows that the graviton can be emitted or absorbed by this subspace. And so that means that subspace must have mass and energy localized there. And so this leads to this kind of thinking led Joe Polchinski to call this space as branes. And you have D2 brane, D1 brane, and D0 brane, etc., depending on the dimensionality of these spaces. And so now you have this description of these D branes in terms of open string. And since these D brane, so for example, in the case of D0 brane, you have this localized point which carries energy and mass. So if you have several of them, you have more energy and mass, and eventually you can create a black hole in this way. But the advantage of this description is that now you can actually describe microscopic property of the resulting black hole in terms of dynamics of this open string. So Andy Strominger here and Qumran Buffer following this idea of Joe Polchinski, successfully quantized open string on this D-brane and extracted the degrees of freedom and derived counted the number of microscopic states on this black hole and derived Hawking's formula for entropy in certain cases of black hole. So that was sort of one of the shining achievements of string theory, that you can actually explain this Wittgenstein-Hawking entropy of black hole, which were sort of conjectured based on macroscopic and low energy derivation of Hawking, being explained using string theory in a more microscopic way. So maybe I should stop the internet access, because I never know who's going to be talking to me. So let me terminate this. Okay. So in this way, the physical phenomena on the event horizon of the black hole can be described by quantum theory of open string corresponding ending on these D-branes. And but this leads to some peculiar. This is rather peculiar situation, because if you look at the left side, you have a black hole which is intrinsically gravitational phenomena, and in fact the dynamics of geometry on the left side are described in terms of gravitational theory. But open string theory does not contain any gravitons. Gravitons in string theories are included in the excitation of closed string. So that means that the description on the left side, right side, does not contain gravity. So this means that the gravitational phenomena can be described by non-gravitational theory, which are localized on the horizon. And it was insight of Franz Maldacena who noticed that by sharpening this correspondence, you can actually show that the gravitational theory in anti-Noether space, here I'm actually describing this negatively curved space in terms of one of the drawing of Escher, is equivalent to conformal field theory located on the boundary of this space. And using this description, so this is called AdS5 X correspondence, and using this description, the evaporation of the black hole by Hawking radiation can be described by unitary time evolution in conformal field theory. And so this actually gives essentially a resolution to the black hole information paradox that was posed by Hawking. And this idea has been very influential. So last year, 20th anniversary of AdS5 correspondence was celebrated. AdS5 correspondence was proposed in 1997. And so for the last 20 years, it has provided lots of insight into string theory and quantum gravity, and some of which we will see in the second half of my talk. And also this AdS5 correspondence has had many applications in condensed matter physics, hadron physics, etc. But today I will not discuss that. Rather, I will focus on the fact that this AdS5 correspondence defines a consistent quantum theory of gravity, including its non-perturbative effect. And I'm going to utilize this description to discuss some of new insight into quantum gravity that we can derive from the holographic principle. So before we get into this, I would like to first tell you some of the insights that we have gained about the nature of space-time and its relation to entanglement in a quantum mechanical state in the next few slides. In string theory, it seems like every 10 years or so, there is some important new progress or new insight emerged. So depending on the point of view, this year is supposed to be the 50th anniversary of string theory. So 50 years ago, Gabriele Veneziano proposed dual, so the expression for the amplitude, which has duality property, which was subsequently explained in terms of string theory. So one can, depending on the point of view, one can say that this is actually 50th anniversary of string theory. Around mid-70s, John Schwartz, Joel Shark, and Tamiaki Yonea discovered that this string theory, which was originally invented to describe hadronic interaction, contains gravity. So that was a very important insight. And then about 10 years later, 1984, Michael Green and John Schwartz discovered that discovered the anomaly cancellation mechanism in string theory. So, and that has opened up a way of incorporating standard model of particle physics in string theory. And that has led to many important discoveries like Calabi-Yau compactification, heterotic string, etc. And 10 years later, in the mid-90s, 1995, Ed Witten proposed duality relation, strong-weak duality relation between various string theory. And that has led to more modern developments such as D-branes and AdS-CFT correspondence, etc. So you can ask what was the important development in the 10 years after that, in the mid-2000s. So depending on the point of view, that was a discovery of Ryu-Takayanagi formula, I should say. So Ryu-Takayanagi formula, which was proposed in 2007, actually opened up the way to connect geometric question about space-time and gravity to question about quantum information theory. And we are now beginning to see the fruits of these discoveries. So now we are getting into middle of 2010s. So it is up to you to discover the next breakthrough. But before we get to that, let me discuss the consequence of this discovery 10 years ago. So let me first briefly prepare some language. So notion of quantum entanglement, I think, well, one of the places this was first realized was a famous paper by Einstein, Podolsky, and Rosen. I think the term quantum entanglement itself was actually coined by Schrödinger, if I understand it correctly. So here is some very simple example of quantum entanglement. Suppose you have two Hilbert spaces, each of which is two-dimension. So suppose you have these two states for each of these Hilbert spaces. And let's take the tensor product of this Hilbert space. So when you have a state like that, which is totally factorized, we say that these two states don't have entanglement. This is the opposite of such situation, where we say that these states are maximally entangled. And in fact, these states are often called EPR state or Einstein-Podolsky-Rosen states. And sometimes it's also called Bell pairs. Now, so I said here colloquially that this has no entanglement and this has maximum entanglement. But it would be useful to quantify how much entanglement so particular kind of state has. So one of the way to quantify it is to use entanglement entropy. So suppose you have a state in this kind of tensor product Hilbert space, and suppose you start, so you take any state, so it can be this state or it can be this state. You take any state, and then you first take a partial trace over the second Hilbert space. And then you get some kind of density matrix here. And then what we are supposed to do is to calculate the von Neumann entropy for this density matrix. So you can actually, easy exercise to show that if you have this kind of factorized state, then entanglement entropy is 0. Whereas if you have EPR state, entanglement entropy is 1. in this case, you can actually see that this is actually the maximum value of the von Neumann entropy. So this is one of the ways to say that the EPR pair is actually maximally entangled. So this was entanglement entropy. So in some sense, so there are various ways to intuitively understand entanglement entropy. I think one of the ways that I like is to say that entanglement entropy basically tells you how many EPR pairs you have for a given state. So to see that, I note that suppose somebody give you any state and calculate entanglement entropy, you can actually understand it in the following way. So suppose you take n tensor product of these. Then you can actually perform some operation called local operation and classical communication, which is essentially to perform unitary transformation on each side separately, which does not change the entanglement property, and also do some classical operation on it, which does not change entanglement property. But then using this, you can actually transform this into just a tensor product of EPR pair. But the number of EPR pair is actually proportional to the entanglement entropy. So in this sense, the entanglement entropy roughly tells you how many EPR pair you have for a given quantum state. So this would be a useful way to think about entanglement entropy. So now coming back to this holographic principle. So if you have AdS, according to the AdS-CFT correspondence, the gravitational theory in this anti-zeta space is equivalent to conformal field theory on the boundary. Now, for this, so here is a Cauchy surface for the conformal field theory. Suppose you divide this Cauchy surface into two segments. One is this subregion, and the other is complement. And then we can, so since quantum field theory is defined locally, so you can decompose this total Hilbert space of conformal field theory to be roughly a product of those that are associated to this region A, and the one associated to this region A bar. Well, there is difficulty in making this decomposition, especially at the boundary and when you have gauge theory. So I have actually a lot of things to discuss about it, but today let me just mention that there is actually a subtlety here and move on. So suppose you make such a distinction, such a decomposition of the total Hilbert space into product of that associated to A and A bar, then you can actually decompose a state on this Hilbert space into this kind of product. And you can repeat this exercise of considering this partial trace over this Hilbert space, which is now Hilbert space over A bar, and then calculate the von Neumann entropy to define entanglement entropy. And it was this paper by Ryu and Takayanagi about 10 years ago, where they proposed that this entanglement entropy is proportional to the area of minimum surface subtending A. So here is this picture. So you have this region A for which you are calculating the entanglement entropy. So suppose you have a state, such as a vacuum state or any other state, which has holographic description in terms of geometry inside of AdS. Then they claimed that the entanglement entropy associated to this region is obtained by considering minimum surface on this space-like slice, ending on the boundary of A, calculates that and divide by 1/4 times g Newton, just like Bekenstein-Hawking entropy formula, except that now this area is not the area of horizon, but area of this minimum surface associated to this region. So by now, there have been lots of evidence to support this, and in some sense, there is even a derivation of that, which I will briefly review later. So this formula has led to lots of interesting insight into state in conformal field theory, which has holographic description in terms of Einstein gravity and in terms of space-time geometry. By the way, if you have any question during, I should have said earlier, but if you have any question during this you shouldn't wait until the end of this lecture. You can always raise your hand, and I'd be happy to answer any question. So this idea has led to a lot of interesting insights. So let me mention one. So suppose you consider a state in one conformal field theory, which is at finite temperature. There is a standard trick in quantum field theory to describe a finite temperature state as entangled state of two Hilbert space of this type, which is called thermofield double. So suppose you have a Hilbert space HA, and suppose this is the energy eigenstate of that Hilbert space. And if you are interested in constructing finite temperature state for this, what you can do is you consider this kind of particular entangled state. It's called thermofield double state. And then you can easily see that if you take partial trace of this thermofield double state over this second Hilbert space, you obtain the mixed state, which has a form of finite temperature state. Okay? So this is called thermofield double state. And thermofield double state has a parameter, which is a temperature. And when temperature is small, well, so any finite energy excitation is suppressed exponentially by this factor. So it goes into this factorized state of the vacuum state. On the other hand, when the temperature is large, then for all states whose energy is much less than kT, it's summed over in this very flat way. So this is in some sense very maximally entangled. So that means that as temperature goes up, the two Hilbert spaces associated to the thermofield double get more and more entangled. So you can, yes? Well, I'm coming to that in the next slide. So far in this slide, I'm only sort of describing statement. And this is true in any quantum field theory. So this is true statement for any conformal field theory, and in fact, any quantum field theory. In any quantum mechanical system, this is a true statement. But as you said, in the case when this is a conformal field theory, and when this conformal field theory has a holographic dual, then you can think of this thermofield double state as eternal black hole in uncertain space. This was pointed out by Juan Maldacena, where he proposed that, well, if you look at the Penrose diagram of eternal black hole, where you have this horizon and you have a singularity. So we know that if you have a black hole, this is a region outside the black hole, but you can actually do the analytic continuation of the geometry. In the case of a black hole in flat space, you have a Kruskal extension. And then you can go inside and you can find new asymptotic region. In the case of conformal field theory, in the case of anti-eta space, it turns out that you have two asymptotic regions. And Juan Maldacena proposed that these two asymptotic regions correspond to two Hilbert spaces, which you use to construct thermofield double state. So in AD, if this conformal field theory has holographic dual, then this finite temperature state can be thought of as an eternal black hole, which has two asymptotic anti-eta regions. And as I showed over here, that as temperature goes up, the entanglement of the two Hilbert spaces in thermofield double becomes stronger and stronger. In this picture, in the AdS side, it turns out that in the same limit when the temperature goes up, the size of the Einstein-Rosen bridge becomes larger and larger. Spatial section over here, you have actually smooth surface connecting this side of the black hole to this side of the black hole, which is called Einstein-Rosen bridge. And the diameter of the Einstein-Rosen bridge is actually precisely equal to the entanglement, the area of the Einstein-Rosen bridge is precisely equal to, according to Ryu-Takayanagi formula, to the entanglement entropy of this sum field double state. So you can say that entanglement is realized geometrically by the size of Einstein-Rosen bridge. So curiously, actually, Einstein and Rosen paper was published exactly in the same year as Einstein-Podolsky-Rosen paper, just 2 months, well, actually less than 2 months in between. Well, it's not clear whether Einstein realized this when he was writing the paper. You never know. But more recently, Juan Maldacena and Susskind, based on this, Lenny Susskind, based on this idea, proposed that, in fact, this Einstein-Rosen bridge are closely connected to this quantum entanglement in a more general situation too. But but at least in this particular setup, one can say that the entanglement entropy, entanglement of these states, sum field double states, is physically realized in terms of the size of the Einstein-Rosen bridge. So now, so this is very interesting. So that means that actually so one of the things that this suggests is that as entanglement between the two Hilbert space becomes stronger and stronger, the Einstein-Rosen bridge becomes bigger and bigger, and in some sense, geometry is being created by the entanglement of the two Hilbert spaces. So we can see that there is a close connection between how geometry emerges in the holographic principle and the entanglement of conformal field theory in the boundary. The Ryu-Takayanagi formula also motivated a very interesting recent development called bulk reconstruction, and in particular, entanglement wedge reconstruction. So there have been many people who are involved in this idea. In particular, Papadodimas and Raju had a very important early insight into this program. So the idea is that according to the AdS-CFT correspondence, anything that happens in the bulk of AdS geometry can be described in terms of conformal field theory on the boundary. So that means that a holographic state in the bulk corresponds to state in the conformal field theory, and local excitation in the bulk, such as creation and annihilation of particle or propagation of several particles, can be described by some operator acting on the boundary conformal field theory. But in fact, there is more refined correspondence, which is called subregion duality in some literature, which is the following. That suppose you have this, suppose you pay attention to some subregion of conformal field theory. Then you can draw Ryu-Takayanagi surface over here. Then there is a subspace of this Cauchy surface of the bulk, which is sandwiched between these two, delineated between these two surfaces. And the statement is that any local excitation, any local operator in this subspace can be realized by operator acting on this region only. So this is sort of refinement of this idea. So there is more detailed correspondence between operator in this region and operator acting only on this region. And so this has been actually such operators have been explicitly constructed by Hamilton, Cabot, and Lifshitz. And then there have been lots of clarification of this idea and expansion of this idea later. But this leads to some, yes. You can use a microphone.
Sure. The entanglement entropy of A and A complement, they happen to be equal if we are in the pure state, in the ground state of the CFT. So, I mean, in that case, the Ryu-Takayanagi surface of A complement is the same as the Ryu-Takayanagi surface of A. So, does that say anything about the rest of the subregion in CFT?
Yeah, so that is, again, I'm going to discuss something related to that. So this has been verified, but on the other hand, this has raised some interesting paradoxes. So let me mention some of these paradoxes. So the claim is that any local operator in this region can be constructed by some operator acting on this A only. But there are a couple of paradoxes that comes out from that. One is that suppose you have local operator acting on this region of the space here. This can be covered by various different entanglement wedges. So for example, you can consider this blue region, which is sort of entanglement wedge of this region, or you can consider this red region, which is an entanglement wedge of this region. So that means that this same operator in the bulk can have different realization in conformal field theory. So why we don't have a uniqueness of operator? Why is it possible that same operator can be realized by different type of operator acting on the CFT? Where is the duality between them? There is also a very peculiar paradox. So suppose you have a local excitation in the middle. Now consider the boundary space, but divide the boundary space into several segments. So that means that any operator you can realize in this region can only realize bulk operator in this region. Any operator in conformal field theory you can utilize in this region can only realize operator in this region. Any local operator you can realize in this region can only realize operator in this shaded region. So they all miss the operator over here. So that means that any local operator on the boundary should commute with this operator. But this is contradiction of the Weizmann axiom of quantum field theory. That Weizmann axiom says that if you have an operator that commute with any operator on the space-like surface, on a given space-like surface, then that operator has to be trivial, namely proportional to an identity. Yes. Yes. Yes, but here I'm just demonstrated that I'm free to divide the space into any small segment as far as we are only interested in local operator. Here I'm making a statement that if you are only interested in operator acting locally in conformal field theory, then I'm free to divide the space into this segment because I'm not losing any operator. But if I divide this boundary in this particular way, then you can see that any local operator, every local operator should commute with this operator by construction. So that would be a contradiction because that means that the local operator in the bulk should be proportional to an identity. So these two statements are very funny because on one hand, you are saying that this local operator is proportional to an identity. But on the other hand, such operator is not unique in conformal field theory. So what's going on? So this is a paradox. So this paradox was resolved in a very nice paper by Haley, Dong, Harlow, and subsequently longer paper by Harlow. And so they pointed out that when we talk about entanglement wedge reconstruction and the holographic duality, etc., we are not considering the total Hilbert space of conformal field theory, but we are considering particular subspace of conformal field theory, which corresponds to smooth geometry and also some local excitations of particle over that geometry. And they point out that this subspace, so you are considering some particular subspace of excitation of the gravitational theory in the bulk, which would correspond to particular subspace on the boundary conformal field theory. And they pointed out that this subspace of conformal field theory has a particular type of quantum entanglement. And these are the type of entanglement which are exactly utilized in quantum error corrections in the quantum information theory. And in some sense, in this subspace, these regions are highly entangled. This region and these regions are highly entangled with each other. And in the quantum information theory language, they are called to be sharing some quantum secret keys between them. So in a situation like that, the particular operator in the bulk, so in this case, what you are having is that you have a Hilbert space of conformal field theory. But then you have some particular subspace, which is called cold subspace. which is used in this quantum error correction. And on this code subspace, it is on this code subspace that these operators are realized. So there is an operator, there is a bulk operator acting on this code subspace, and you are asked to realize this operator as an operator in conformal field theory. And such operator can have actually multitude of realization. And so that means that the realization of the operator is redundant. And that is exactly why actually such representation is useful in quantum error correction, because one of the ideas of doing error correction is to introduce redundancy in the information. So having redundancy helps because that means that even if you lose some of the qubit, you can reconstruct it. And so this exactly explains why you have this kind of redundancy. And the fact that this operator creates states which are highly entangled means that within this subspace, even though the statement of Weizmann axiom is actually about the whole Hilbert space, and but within this error correcting subspace, code subspace, you do not get to this kind of contradiction. So this led to explanation of both of these problems. So I would like to actually utilize this type of insight to derive some statement about the quantum theory of gravity, at least in the anti-digital space. So I'm interested in this kind of question because of the Swampland question. So Swampland question, let me first formulate it. You can say it in the following way. So suppose you have an effective theory of gravity, such as Einstein gravity coupled to a particular set of matter. You may want to know whether it is realized as a low energy approximation to a consistent quantum theory of gravity with ultraviolet compression. Can you always do that, or is there a reason that you do not believe that that is not possible? So that is a question. So let me go back to one of the questions that I raised at the beginning of this lecture. So at the beginning of this lecture, I raised 3 problems which you encounter when you try to quantize gravity beyond the Planck scale. And one of the questions is that is Einstein gravity guaranteed to have ultraviolet compression? As I said, in the case of quantum field theory, you can liberally write any low energy effective theory and hope that have a UV compression. But in the case of quantum theory of gravity, that may not be the case. And if there are actually certain conditions for low energy effective theory of gravity that has to be satisfied in order to have UV compression, that's a very useful thing to know, because that means that we can actually make predictions by utilizing it. So that would be a very interesting thing to know. So that is a Swampland question. So Swampland question is to come up with some criteria for low energy effective theory that has to be satisfied in order for those low energy effective theory to have UV compression. So can we come up with such idea? So I would like to sort of focus on the type of conditions that are related to the symmetry. So in fact, in quantum theory of gravity, there are 2 well-known conjectures. One is that quantum theory of gravity has no global symmetry. All the symmetry in quantum theories has to be local gauge symmetry. And the other conjecture is called the completeness hypothesis, which is that if you have a low energy effective theory of gravity, suppose which contains compact gauge group G. G may be, when I say compact gauge group, it can be either compact Lie group or it can be finite group. In the case of discrete group, if you use appropriate topology, the finite group are compact. So then, if in those compact group, the conjecture is that there are physical states in every finite dimensional unitary representation of a group. So for example, if you have a U1 gauge group, and if the U1 is compact, you have electric charge and magnetic charges, but they have to satisfy Dirac quantization condition. So in the case of quantum field theory, so that means that electric charge and magnetic charge make some kind of lattice, satisfying the Dirac conciliation conditions. In the case of quantum field theory, this lattice does not have to be filled. That there can be, you do not have to have particle for every pair of electric and magnetic charges that are consistent with Dirac conciliation conditions. But this conjecture says that in the case of quantum gravity, all possible charges must be realized. So this is called the completeness hypothesis. So one of the purposes of this particular work that I'm going to describe is actually to prove this conjecture in the case of AdS correspondence. So, but before going into that, let me actually review the standard argument for this conjecture. So we say that there is no global symmetry in quantum gravity because of the following reasoning. So suppose you have a continuous global symmetry G, like SU2 group or SO3, suppose you have such group acting on the low energy effective theory, and that is exact. So that leads to contradiction. Because suppose you combine various kind of matter field carrying SU2 charges and make black hole. So by throwing in matter of various charges, you can construct a black hole which carry large dimensional representation of this group. For example, SU2 can have arbitrarily large spin. So if you have spin J representation of SU2, you have dimension 2J plus 1, and they are all degenerate because it's a symmetry. Now suppose I Hawking radiate this black hole. But let's keep the mass to be much larger than Planck mass so that we can still use the Einstein gravity description. But then such black hole should have Bekenstein-Hawking entropy, which is large but finite. So that leads to contradiction. Because since Hawking radiation is G-blind, that means that if you have the total charge of the Hawking radiation should be neutral. So that means that even after the Hawking radiation, you still have the same dimension of the representation. So that means that if you had very big representation to begin with, and if you Hawking radiate and make the mass small, and therefore entropy small, then you can get into a contradictory situation where the dimension of the representation of the group required for the consistency is bigger than the maximum dimension of the state you can have by the Bekenstein-Hawking entropy. So that is sort of one of the standard arguments. Yes? What do you mean by asymptotic symmetry? So in the case of I'm going to define precisely what we mean by symmetry. The kind of symmetry you mentioned is a global symmetry from the CFT point of view, but is a gauge symmetry in the bulk. So in the gravitational theory language, those are gauge symmetry. So that's not excluded. In fact, those plays an important role later. So this is a standard argument, but this is actually not totally satisfactory. You can actually put various issues with this. And one of the problems is that we don't know what happens to discrete group. For example, suppose you have Z2. Z2 only have one-dimensional representations. So this argument does not work. And there are also some details that is not very clear. For example, Hawking radiation is G-blind, you say. But there can be some subtle correlations in the radiation that may, and then representation may leak out and things like that. So it would be nice to have a more sort of robust argument to exclude this kind of possibilities and applicable to discrete group, which our argument will work. So this is actually work in progress with Daniel Harlow, and we are actually writing up a paper on this. And in this work, we are going to show that any global symmetry in anti-Utah space is inconsistent with locality property of conformal field theory. And compact symmetry, symmetry of conformal field theory. It can be discrete or continuous. Correspond to gauge symmetry with the same group. And in the gravitational theory with gauge group G, there must be physical state in every finite dimensional irreducible unitary representation of G. This is a completeness property. And with some additional assumption, we can also show that the symmetry of conformal field theory has to be compact. But today, let me focus on this first statement. So before we get into the derivation, let me first define what we mean by symmetry. So I say global symmetry. The way that we learn symmetry, definition of symmetry in undergraduate quantum mechanics is the following. So symmetry, we say that Hamiltonian has a symmetry if there is a group, so that for any element of the group, you have a unitary operator acting on the Hilbert space, realizing this group and commute with Hamiltonian. So this is what we mean by symmetry, how we learn symmetry in undergraduate. But in the case of quantum field theory, this is actually not very satisfactory because this definition does not include the locality property of quantum field theory. So for example, if you consider projection operator for the 42nd eigenstate of Hamiltonian, and then use that to rotate Hilbert space, that certainly satisfies this condition. But that, by any means, but that is not local at all from the point of view of quantum field theory, and we cannot actually exclude such global symmetry. So we are not going to consider such thing as a symmetry of quantum field theory. So I'd like to actually define global symmetry of quantum field theory, incorporating locality ideas. So here is our definition. So the first three statement is not controversial. So we say that the symmetry should map a local operator to a local operator. And symmetry should be faithful on a set of local operator. Namely that if you have a if you have a group, therefore any element of the group, there is at least one local operator which has non-trivial commutation relation with that symmetry. And the symmetry should, of course, commute with energy momentum tensor. So those are the statements that is sort of very, we are very familiar with. But we have actually a third requirement, which is to say that for a set of open disjoint subspace of Cauchy surface, we can have, if you have, say, suppose you have a subspace R1, R2, R3 on the Cauchy surface, then for the operator that is acting on this subspace, you have this kind of property that you can define operator acting on this subspace, which acts local operator in this way. And then if you are interested in defining operator, symmetry operator acting on this region, then you can decompose it into this way. If you have actually continuous symmetry for which Noether theorem works, then this is actually triviality. Because if you have a local operator, if you have a Noether current, J, and you can, if you can define symmetry generator acting on the region as exponential of Noether current in this way, then clearly, if the region is a union of the two regions, then you have this integral over this union. So it becomes a product of this region. Right? So if you, you have a Noether current, then this property is a triviality. But we would like to have a statement that works for both continuous symmetry and discrete symmetry. And for discrete symmetry, we don't have Noether theorem. So this is sort of a substitute of the Noether theorem. And in fact, there are actually a group of people in algebraic quantum field theory who actually looked into that. And they show that for continuous symmetry, if the first three statements is true, Noether theorem guarantees the fourth statement, but they show that more generally, under the what is called the splitness property of quantum field theory, which roughly says that Hilbert space can be decomposed into product of subregions, then this is actually true. So this follows from the following simple sort of theorem in linear algebra that you can actually derive. So suppose you have a Hilbert space, and suppose the Hilbert space decomposed into, actually this is meant to be tensor product, so please excuse me. Decomposed into tensor product of Hilbert spaces. And suppose you have a unitary operator acting on this Hilbert space. So suppose you have a local operator, and if unitary operator acts in the following way, so for any operator acting non-trivially only on the one of the Hilbert space component, this unitary operator acts in such a way that its conjugate also acts on the same Hilbert space only. Then you can show that this unitary operator decomposes into product. So this shows that if the Hilbert space splits into this way, then unitary symmetry operator always decomposes in this way. So sorry? Yeah, so we can discuss that, but it is true statement. So the split, gauge theory can have split property, and actually split property is rather sort of broad notion, and with appropriate UV completion of the theory for large class of quantum field theory, this is true. So with this preparation, we can actually prove, using this entanglement wedge reconstruction, we can prove that global symmetry in the bulk is in contradiction with this local property of quantum field theory. So let me give you an argument. So suppose you have a gravitational theory in uncertain space, and suppose this gravitational theory has a global symmetry G. So that means that there must be a bulk local operator that transforms non-trivially and faithfully into another local operator at the same point. No, here I'm defining global symmetry on any theory. Yeah, so here, in the case of bulk, the local operator, here we accommodate the size of Planck scale so that you can have gravitational dressing, for example. What do you mean by polynomial of bulk reconstruction and code subspace? It was already assumed that we have some appropriate notion, approximate notion of local excitation in the bulk. And when we say global symmetry in the bulk gravitational theory, so what we assume is that those local, approximate local excitation in the bulk should be a faithful should give a faithful representation of the symmetry. So that's the assumption. And so if you take into gravitational effect, you cannot have exact local excitation. And so this allows actually some finite size. In fact, some of the states that carry this representation may be a black hole. And our argument actually can be used to disallow such situation also, as you will see. So I should have said, but this definition of global symmetry is going to be used both for the boundary CFT and bulk gravitational theory. And thank you for pointing this out, because we would like to use this definition to say that bulk gravitational theory with this global symmetry is not allowed. And the reason for that is that suppose you have a global symmetry in the bulk gravitational theory, then by definition, you have to have local excitation in the sense that we discussed, which transforms into each other non-trivially under the action of the group. But then you get into immediately a problem, because such operator, as you move to the boundary, can create operator which faithfully represent symmetry on the boundary. So the boundary theory should also have the same symmetry. So then on the boundary, the symmetry generator can be decomposed into these segments. And each of these segments has entanglement wedge of this region, and none of which touches this local operator in this way. And you can say that this may have a big size, this may have a bigger size, like Planck scale size, or sometimes these can even be black hole of finite horizon. But if you can actually, I'm free to cut this into as small region as possible. I can have this region to be very large number. So that means that even if this has a big size, I can choose the boundary segment to be very small so that their collective entanglement wedge would never reach to this region. So that means that this symmetry operator commute with this operator. So this is a short argument to say that this is actually contradiction. So this excludes, this proves that any global symmetry in AdS is inconsistent with locality of conformality theory. And then I don't have time, I only have like 3 minutes, so I don't have time to explain the rest. But there are sort of, we can actually utilize similar argument to exclude other possibility too. So since we are talking about Swampland question, I cannot actually, I should also talk about the weak gravity conjecture. So weak gravity conjecture is the following conjecture, that in any low energy theory described by Einstein gravity coupled to Maxwell field and coupled to finite number of matter field, if the theory has ultraviolet completion as a consistent quantum theory, there must be a particle with charge Q and mass m much less than Planck mass, such that this inequality is satisfied. This inequality essentially says that the Newton force between that particle is smaller than the Coulomb force between them. So this means that if you have a Maxwell field, then there must be at least one particle, and for that particle, Coulomb force is stronger than the gravitational force. So that's the reason for this name, weak gravity conjecture. So weak gravity conjecture has been motivated, as far as I know, based on these 3 reasons. One is the black hole physics, which is very similar to the argument that I gave at the beginning for the absence of global symmetry. And but this argument has some holes. But I think that more important reason is that in all known construction in string theory, this is true. And there is also holographic motivation, which I would like to now mention. So here is a holographic motivation for weak gravity conjecture that was actually pointed out by Daniel Harlow. So the argument goes as follows. So suppose you have AdS5 geometry. Then, as I mentioned, this is holographic dual to Sommerfield double state. So that means that any operation you can do in AdS gravity in this Schwarzschild geometry, one should be able to do that on the Sommerfield double state. So suppose you have a Wilson line going through the Einstein-Rosen bridge, acting on the both Hilbert spaces. So then you have an operator acting on the both Hilbert space. But since the Hilbert space, the 2 Hilbert spaces are just tensor product, so that means that any operator acting on it, one should be able to write it as sum of products of operators acting on each of these Hilbert spaces. So that means that one should be able to cut this Wilson line operator into half, one acting on this side and the other acting on this side. So the only reasonable way that one can think of that something like that can happen is that actually this gauge field in the bulk, which is responsible for this Wilson line, is emergent. So there is some kind of energy scale below Planck scale, so lambda, so that the gauge degrees of freedom is actually emergent. So one can actually argue rather convincingly that if you have emergent gauge field in the bulk, then weak gravity conjecture actually holds. So suppose, let's consider, for example, the CPN model. And CPN model, when n is large, has a phase in which you have U1 Maxwell theory coupled to the charged particle. And you can calculate the charge, and if n is large, it renormalizes a Newton constant too. And then you can show that weak gravity conjecture is satisfied in this case. And actually, recently, Daniel Huar and I actually generalized this to the case of multiple U1. And in the case of multiple U1, there is actually generalization of weak gravity conjecture by Chen and Remen involving convex Hull conditions. And we were able to show that convex Hull condition is also derivable. So, but in all these cases, actually the weak gravity conjecture is strictly satisfied. So there has always been a question of whether we need equality or not. So when people formulated this weak gravity conjecture, the only reason that they added this equality was that BPS state satisfies it. So that led Coulomb-Buffer and I to conjecture that there is actually a strict inequality satisfied, except for BPS state. And then we noticed that if you actually make this slightly stronger conjecture, then it excludes non-supersymmetric antidata space. We can show that any non-supersymmetric antidata space supported by flux must be unstable. Not flux, flux must be unstable. In fact, it is true that all non-supersymmetric antidata space, there have been several proposals of non-supersymmetric antidata space, but all these IDS are marginally stable at best, and some are unstable in a very interesting way. So let me show you a couple of examples. So I'm actually getting very end of the talk. So let's consider, so this is actually the first example of non-supersymmetric antidata space proposed by Shamit Kachru and Eva Silverstein almost immediately after AdS-CFT correspondence was proposed. So first example of AdS-CFT correspondence was that type 2B string theory on AdS5 X S5 is dual to n equal 4 superamers. They proposed to divide this S5 by some discrete subgroup of SO6. They show that if gamma does not fit into SU3, then all the supersymmetry is broken. However, it turns out that either gamma has a fixed point on S5 or gamma has no fixed point on S5. This construction is unstable. You can show, for example, when gamma has no fixed point, there is actually a Witten's Karuta-Klein instanton, where this, if you have no fixed point on gamma, so that means that there is actually non-trivial S1 in this quotient space. And then there is actually Karuta-Klein instanton constructed by Witten, which actually makes this unstable. So there was actually another interesting example suggested by Martin and Rial, which is actually AdS5 X CP3 in M theory. So when actually Coulomb-Buffer and I wrote the paper, they pointed out this example and asked whether I can exclude this possibility. So I took it as a challenge and looked into that with one of my graduate students. And we actually, in the process, discovered a new type of instability, generalizing Witten's Karuta-Klein instanton. So this turned out to be unstable also. So if this is true, then actually it leads to some interesting phenomenological prediction. So it was actually suggested by Alkani Hamed and collaborator that let's consider standard model of particle physics, this genuine SU3 cross SU2 cross U1 theory. Suppose you compactify it to 2 or 3 dimensions, then depending on whether neutrinos are Majorana or Dirac, and depending on their masses, the resulting space has Zojita space or anti-space which are stable. So this is actually a very interesting result. So what happens is that if you compactify this space, then there is a Casimir effect on this S1, which gives rise to effective cosmological constant. And depending on the space is Majorana or Dirac, you get AdS space or Zojita space. So in our paper, we pointed out that if our sharpened version of weak gravity conjecture is true, then it should rule out the non-supersymmetric AdS. So that means that certain type of Majorana neutrino masses, in particular, certain range of neutrino mass should be excluded. So that was what we wrote in our paper. And more recently, Luis Ibanez and collaborator took this more seriously and did rather thorough study and showed that using this sharpened conjecture, there is actually a lower bound on the cosmological constant given by neutrino mass to the quarter, to the fourth. So this is actually a very interesting coincidence. If you look at the current estimate for the cosmological constant based on this accelerated expansion of the universe, and based on the estimate of we don't know the absolute value of neutrino mass, but we know the difference of the neutrino mass. So if the actual value of the neutrino mass is of the order of the difference of the neutrino masses, then the neutrino mass to the fourth is very close to the cosmological constant value. And in fact, this sharpened version of the weak gravity conjecture, combined with Nimar, Kani, Hamed, and collaborators' observation, may explain this coincidence. So this is actually sort of interesting application of this line of thought. So anyway, so what I would like to conclude with this lecture is that in the gravitational theory, we have a very interesting ultraviolet infrared connection. So that leads to some non-trivial constraint in low energy effective action. In order for that to have, for these to have UV completion, so it can give rise to surprising infrared prediction of observable phenomena, such as this one, using consistency of quantum gravity. So studying consistency of quantum gravity can be actually useful exercise in this sense. So another point I wanted to make was that collaboration of quantum gravity with quantum information may provide a very useful idea for us. And it's a very interesting direction to explore. So that's all I wanted to say. But there is one more thing, which is, as Spencer says, that we are going to have a string conference in the last week of June in Okinawa. This is a conference site looking at the beautiful East China Sea. And this Okinawa is actually very conveniently located. It's actually within a couple of hours from almost all major cities in East Asia. I guess from India, you have to fly to either Shanghai or Beijing to get there. And we also have some satellite programs, string mass conference in Sendai a week before, and 1 month program in Yukawa Institute afterward. So these are posters of these two events. So I would like to encourage you to participate in these conferences. So with that, thank you very much for this opportunity.
Thank you, Hiroshi, for a very stimulating talk. We can take a few questions, I'm sure.
Yeah, so that's so I think we wrote something like that in our paper, and so there's a conjecture that, as you said, that conformal field theory with large gap and sparse light, large central charge and sparse light spectrum should have holographic dual. And there are some arguments to say that, in fact, for this CFT, you can do the bulk reconstruction, and there should be holographic dual. So if you assume that, then this conjecture should be excluding that. So that can be a challenge for people in Bootstrap to see whether such CFT can be constructible or not. Yeah. So here we only considered internal symmetries. And so we didn't consider space-time symmetry. Is that what you are discussing? Oh, yeah. Yeah, so we did not consider that. Yes?
So this relation of lower bound to the cosmological constant via neutrino mass. So the neutrino mass, like in many beyond standard model models is understood from some kind of various kinds of seesaw mechanism and so on and so forth. So is is there some understanding? So is the statement that the cosmological constant is also related to seesaw mechanism? Why it is small?
This line of argument does not particularly assume that. And also seesaw mechanism, I think that works for Majorana case, I believe. And but Nima-Alkani-Hamed's argument is sort of more general. It does not assume sort of specific UV completion. And so the argument is that if you compactify on the circle, then you actually assume that in 4 dimension. So in this particular paper, for example, you assume that in 4 dimension, somehow, so 4-dimensional cosmological constant must be fine-tuned to be the present value. So that is the input. So in 4 dimension, of course, you don't know why cosmological constant is a value that we have now. We don't have a microscopic explanation. So you use that as an input. So that means that there are various Kashmir effects, there are various one-loop effects that can contribute to the cosmological constant. But there must be a conspiracy in such a way that there are various cancellations and you end up with a current value. So that's you assume. Now, suppose you compactify the theory, then on the top of that one-loop effect, there is actually a one-loop effect that depends on the radius. So that's a Kashmir effect. And neutrino has particularly dominant contribution to this radius-dependent Kashmir effect because neutrinos are lightest particle and that gives a dominant contribution. So the only information you need to calculate 3-dimensional cosmological constant is the type of mass of neutrino, whether it's Dirac or Majorana, and the actual value of neutrino mass. And then using that, you can calculate 3-dimensional cosmological constant using 4-dimensional cosmological constant and neutrino mass as an input. And then in some range of mass, so there are some inequality between the 4-dimensional cosmological constant and neutrino mass. If they are satisfied, the inequality is actually this. If that is satisfied, then you get 3-dimensional non-supersymmetric ancillary space. So if you assume this conjecture that is excluded, so that means that inequality between the 4-dimensional cosmological constant and neutrino mass is excluded, and so that leads to this statement. So it does not assume any particular UV completion like seesaw mechanism.
For the cosmological constant problem, does it help in any way in solving the cosmological constant?
No. As I said, it doesn't explain 4-dimensional cosmological constant. It's assumed that somehow there is a mechanism where cosmological constant end up like that, either landscape or something. Yeah.
So the weak gravity conjecture is usually motivated by these semi-classical black hole arguments, which you mentioned.
Yes.
And I never really, and it's used to constrain effective field theories if not they're compatible with UV completion. So I never really understood why using semi-classical arguments to extrapolate certain properties or constraints to a full quantum gravity theory is a valid thing to do. So is there motivation to believe that not additional quantum...
So I'm not sure, your question is rather philosophical, but I should also point out that I do not particularly like that argument, but the argument is based on low energy effective. The argument is about low energy effective action. It is not about, so I'm not quite sure I understand your question because I think it's a condition on the low energy effective action where you assume that you are applying it in a case where Einstein approximation is valid. So you assume large black hole where the curvature radius is small, and you postulate existence. You postulate existence of some particle spectrum, and if that particle spectrum does not satisfy the weak gravity conjecture, namely that if the particle spectrum does not contain particle whose charge is greater than mass, then you have some funny property of extremal black hole. So that is a statement. So that statement can be, that line of argument can be stated whether or not that you can buy this argument, but the line of argument itself can be stated within the language of low energy effective theory. So even though I do not buy that argument, but I'm not sure whether your criticism is applicable to that argument.
Any other questions?